Well, welcome and thanks for coming along to watch a video on differentiating log functions. And I've sketched a little log function here, but we're going to add a bit of detail to that. I will say first, I've just made a video on differentiating exponential functions. It's probably best if you know how to do that because it introduces the natural number e. And I need to know about e for this video. So the first thing I will say though is about e. So the natural number e is e, which is about 2.718. Okay, I'm going to be dealing with differentiating y equals log base e of x. Okay, you can differentiate log base 2 of x or 10 of x or a of x if it's another number, but I'm going to be dealing with log base e of x. And it's really important you understand where the e comes from. But more importantly, I want you to know that this can be written as ln of x because it's called the natural log, and it was actually determined by French mathematicians. So it's log natural of x, and so it's ln, and I'm going to deal with that. So there's our function, ln of x, and a couple, well, my axe is a bit bent, but hopefully you understand it. The point is here that we have some important points. So that one first, have a think about what this point is. Okay, what do I substitute into there in order to get 0 as my y value? And the answer is 1. E to the power of what equals 1, sorry, is 0. So I've got 1 comma 0. Now if x is e, so I'll put e here, then this point here is e comma 1. And there's a few other important points, but I'll just stick with those two for now. They're really the important ones that we usually talk about. You'll note though that if you do a bit of this on your computer, it looks very exponential because log is actually it's basically the opposite to exponential functions. So a log graph is the reflection of an exponential graph over the line y equals x. Because if I swap y and x here and then rearrange, I get the exponential function. So there's another point to consider. Anyway, there's my function. This is here, and I want to derive y equals log x to see what the rate of change is. And we're going to do it again by investigating what happens on our graph as we consider the gradient. So let's have a look. First of all, down here, our graph doesn't exist here. Our graph doesn't exist for any value, that was about to write y, so x is less than or equal to 0. You cannot put a negative or a 0 into a log. It just doesn't work. Not unless there's some transformations that are taking place, like if it's x plus 10 you could put negative 3 in, but at the moment there's not. So that's really important. So there's no gradient there. So we won't be dealing with anything on this side. Here, at these little numbers there, the gradient's massively steep. And it's positive. See how the gradient's positive here? Positive, positive, positive. It's always positive. The gradient's always going to be above here. It's always positive. But here it's massively steep. So it's up here. And as we move along, it's still steep, but it's just a little bit less steep. So it's there. And a little bit less steep. And a little bit less steep. And as we get to here, somewhere, the gradient becomes 1. So let's say it's there. And then the gradient is getting smaller and smaller. You can see this flattening out. Now there is no horizontal asymptote to a log function. So it will never actually reach 0. It just keeps on going on. And I'll sketch these, I'll connect them together, and you've seen how bad I am at connecting dots, but anyway, there we go. If I sketch those, we get this function. That's our gradient function. That function there is actually called a hyperbolic function, and it's y dash equals 1 over x. That's the version of a hyperbolic function. Now obviously there's some variations if you've got some constants in your log, but it turns out that if y equals the natural log of x, then dy dx, so that didn't come up, dy dx is equal to 1 over x. Magic. And so I'll put a box around this because that's our important rule. You just need to apply that rule to chain rule questions, product rule questions, quotient rule questions, etc. You know, where you've got constants involved and stuff like that. I will talk about a nice little result though. It's just something that I found people sort of get a bit put off by when it happens to them, and they're like, oh, what's just happened here? So, what if we're deriving y equals the natural log of 7x? And I'll put brackets around it to make sure you know that 7x is inside there, okay? Now, this is actually a pretty simple chain rule question. So let's imagine I go through this. Dy dx, I'll do it not using the full chain rule, but I'll do it with the setting out to show each step. Now, when I derive log of something, I get 1 over that something. Okay, I'm doing the outside function of the chain rule, so I get 1 over whatever that something is. And then I multiply by the derivative of the inside function. And I keep on doing that until my chain rule is run out. So that is d dx of 7x. And when I derive 7x, I get 7. So this is equal to 7 over 7x. And of course that's just equal to 1 over x. And it turns out that if your function is y equals the natural log of ax for any a value, if a is negative, you've got some different issues, it's over this side, blah. Anyway, for any positive a value, let's say, then you just get 1 over x. So it doesn't matter about the steepness, you just always get 1 over x. Or actually that a value compresses. So it doesn't matter about the compression, but you get 1 over x. So that's really interesting. And an important rule just to recognise, because I've seen people, they get to here, they get to there and they're like, whoa, it should be 1 over 7x or something else. It doesn't quite work. Anyway, so there it is, deriving log functions. Go ahead, practice these skills with chain product rules, stuff like that. Make sure you can do them. It is really skill based, but if you understand where it comes from gradient wise, then you'll have enough depth really to apply it. And then it's just going ahead and practicing putting it in context. So that was fun, I think. Have fun.